We're going to start out. I want to introduce Bill Pinnix. Bill Pinnix is a supervisory fish biologist with the U.S. Fish and Wildlife Service in Arcata. He's been studying fish and their habitats in Humboldt Bay, in the Humboldt Bay area since 1993. His early career pursuits included marine fish ecology and the importance of marine zooplankton in fish populations, or two fish populations rather. He received his undergraduate degree from Humboldt State University when it was still Humboldt State in 1995, and then moved on to the University of Washington School of Fisheries to pursue his master's, where he studied climate forcing mechanisms of the nearshore marine environment on coho salmon survival, and he also worked on some coho harvest forecast modeling, which is a fun parallel because it's very similar to my graduate work at Humboldt State. Following completion of his master's, he continued his research on climate forcing mechanisms in the marine environment on fish and zooplankton, and then returned to Arcata in 2001 to work for U.S. Fish and Wildlife Service, where he's currently at in a different position. But he's done extensive work on monitoring numerous fish species in freshwater and marine environment. I actually remember the first time I met Bill. He probably doesn't remember this, but out at Freshwater Creek, he was doing acoustic tagging, and we were catching coho salmon and giving them the biggest ones we had, and they were cutting them open and suturing acoustic tags in them with Pete Nelson, who I later worked with in consulting. So some good connections there. So he serves on multiple technical advisory committees, and he's especially proud of his work with the Pacific Marine and Estuarine Partnership. He currently serves as the lead of the Monitoring and Assessment Division of the Fish and Aquatic Conservation Program at the Arcata Fish and Wildlife Service. And that, I'll hand it off to Bill.
Thanks, Ken. And thanks you all for staying awake. I know it's the napping hour after lunch. So hopefully I don't put you all to sleep. They asked me to speak about fish populations, juvenile fish, adult fish. So I wanted to say that this data that we've collected, it's not mine alone. So this presentation, I'm just accumulating slides and data presentation from a number of different studies. Who in this room has ever worked in the Trinity River on outmigrant monitoring? Keep your hands raised. Who has done any adult monitoring? Who's done anything related to that? It's like more than half the room. So thanks to everyone here. I mean, these are the people that worked hard to get this data, do these analyses, and what I'm going to present here. So again, I'm just relaying this information, and hopefully we'll get across some points that for salmon populations, it's not all doom and gloom. We have some successes to celebrate. There are some positives, and so want to we just have to remind ourselves the good work that we've done. So brief outline. Going to talk about adult Chinook salmon. So focus is going to be Chinook salmon. Now, last night Mike Dickens said you got to make sure to talk about steelhead, and I'm like, sorry, too late. It's only Chinook today. So I'm going to talk a little bit about kind of abundance through time. Talk about how the abundance has changed, but also how the demographics, so where these fish are in the river, where they've spawned, and then effects of water management, not explicitly, but blur your eyes and kind of wave your hands. You can make some assumptions about how water's managed and the impacts on these species. Now I'll transition into juvenile Chinook salmon. Again, talk about abundance and then biomass, because that's an important part of the story. Stock recruit relationships, size distribution, and then timing. And again, these are all kind of laid on that fabric of the history of the management of the river, or mismanagement, if we think about gold dredging and the impacts to the aquatic ecosystem. So this is a repeat, but one thing I wanted to point out. So this slide here, that's kind of why we're all here. So we have here, this is Chinook salmon reds. They're spawning in a restoration site. So again, this is a success. We did some manipulation of a site. Salmon came and spawned in these areas. So I think that perspective is important, right? If we take too narrow of a focus, the impacts or low salmon returns can not only be disheartening, but it goes pretty deep. It's like an emotional response. We want to bring back the salmon. So again, was trying to put this all in perspective. And as I go through these slides, there's going to be some very similar slides from one to the next. But it's really important to note that the axes on these, and especially the y-axes, will have different scales. So when I put up a figure that's got some axes, look at the y-axis and say, okay, what is that scale? So when I put up the next one, you're like, oh, okay, that's they're on different scales, and so that's part of the perspective is important on these. So Chinook salmon escapement. So escapement, for those who aren't aware, is a term that fish biologists use that just means those fish that have made it to the spawning grounds to spawn. And the escapement is the part where they've escaped the fishery. So this data that we have comes from a number of different monitoring efforts, both on the Trinity River, but also Lower Klamath. Now I'm just going to pop this slide up. So there's a lot going on here. I'm going to spend a little time. I'm going to point out some things that that I find interesting or of importance. So if we look at the time series, we see an inherent variability. So we see large peaks and we see some pretty low valleys. This time series only goes through 2018. That is in part the result of these figures are pulled out of our adult salmon synthesis report, which there's a number of authors in the audience. And these slides were easy to pull together for this. So what you would see post 2018 is there are also some fairly low return numbers. You can see that since 2002, these estimates of fall run Chinook salmon are composed of both hatchery and natural fish, and in various proportion. On the right hand, you've got the y-axis for the percentage of natural origin, and that's what this line with the black dots represents, is the proportion of these numbers that are natural origin Chinook salmon. So when I was first looking at this, I'm like, man, how am I going to explain how these low runs are not that bad? I mean, it's bad. It's, we've got this restoration program. We're trying to do good for the fishes. But I noticed that I wanted to point out too that so the program has a goal of getting 62,000 fall Chinook salmon into the river to spawn every year. That's kind of one of the goals we're going towards. And if we look back in time in the 80s and early 90s, we surpassed that goal 3 times. But when you look at this figure, those high years sort of make the more recent years seem kind of out of place. But if we just kind of ignore those high years, the variability and the population levels that we see more recently don't look so out of place, right? So perspective matters. And yes, we're trying to get back. We would like to get more of these bigger runs. But if you look at the variability that existed, going back to 78, we're kind of in that ballpark, in the more recent years. So it's not all bad. And then if we look at the kind of floor, like these low runs that have happened more recently, they're somewhat in line with some of these earlier years. They're not unprecedented. I think, what may be unprecedented is sort of like the back-to-back years of low returns, but we've seen that in the early 90s. So again, perspective matters. And if we take a little closer look at the percent natural origin, and in particular, these 3 years here, we're getting close to 90% natural origin fish on the spawning grounds. So there's something that happened in these years. Don't entirely understand what it is, but very few hatchery Chinook made it back to the river. So there was perhaps a differential survival between hatchery and wild fish, between the river and then returns. So there's potentially something there that probably requires some bit more investigating to kind of tease out, like there's potentially a story there that may help us understand more of why we've been getting these lower salmon runs in recent years. So this is fall run Chinook salmon. I'm going to put up spring run Chinook salmon. Similar time series. There's a couple of years where data is missing. I don't think those are zeros. But again, you see a similar sort of variability. What you'll note is that the y-axis is different here, different scale. And then the goal for spawning escapement of spring run Chinook salmon is, around 6,000. So much lower, and we've met that goal more times than we have for fall run Chinook. But again, of concern are these recent years. But and like fall run Chinook, those values aren't necessarily out of the range of availability that we've seen in the past. So that was kind of like the look of the Chinook salmon over time. Now we're going to look at the distribution of the reds or the salmon nests over time. And this, we're going to start with, this is fall run Chinook. So let me explain a little bit about what these figures are. This is years on the x-axis, and again, we're going from 2002 now. So those time periods where we're able to separate out hatchery versus natural fish on the spawning grounds, and this is all of the reds that are surveyed in the entire main stem of the Trinity River. So from Lewiston Dam down to the confluence with the Klamath. And then these are numbers of reds. And so, what we see on the top is that all Chinook combined, there's been a decrease in the number of reds over time with some variability. There's some outliers, or not outliers, but just, some higher years. But you'll note this p-value for the natural origin Chinook salmon is not significant. So this slope for natural origin, although it appears, trending down, it's not a significant negative slope. So it looks like that, at least for natural origin Chinook, things are, holding stable through time. But hatchery origin Chinook, a significant decline, and that decline in the hatchery origin Chinook is driving this decline in all fish combined. And so again, this is the main stem from Lewiston down to the confluence with the Klamath. Now, if we just focus in on the upper 40-mile restoration reach, we see a similar story. It's a decline overall in reds, numbers of reds. Now the decline in natural origin Chinook is just significant at the 0.05 level. So there's a detection of a decline there. The hatchery fish decline, again, fairly steep, persistent decline in the numbers of reds deposited in the restoration reach. But if we take a little bit different view of those areas downstream of the restoration reach, we see that all Chinook red numbers are increasing through time, although I would say mildly significant there. But you'll notice that the natural origin Chinook reds show an increase through time, and the hatchery origin fish are decreasing in that reach as well. So again, this perspective that we're seeing declines in some areas, but potentially gains in other. And another way to look at this is look at the distribution of those reds longitudinally along the river through year. Well, sort of. So what we see is, this now is the mean distance of all of those reds that we count on the river, how far they are from Lewiston Dam. And we've seen that distance has been increasing over time, especially, for natural origin Chinook, but not for hatchery origin Chinook. So the salmon seem to be spreading out and spawning in more areas downstream. I would like to think that is a large part of that is due to our water management and gravel introduction actions on the river. I may be going out on a limb and saying that, but there does appear to be this positive effect, because the closer you get to the dam, the more dense the reds are, the more potential negative impacts you have due to that higher density. And so the next piece I'm going to talk about is pre-spawn mortality. So why is spawning near the dam, why do we want those fish to spread out? So if we look at so pre-rod versus post-rod, rod being the record of decision, that is what the Secretary of the Interior determined along with partners the preferred way of managing water. So if we look at before that water management occurred, which really started getting implemented in 2005, so pre-2005 and then post-2005, that we've seen a large drop in pre-spawn mortality. So again, this is positive. This is a good thing. We've made some progress there. So this is everything lumped together. But if we look at that in relation to the dam, like how, so this is a little bit different. This is like proximity to the dam, right? So these numbers along the bottom are the reaches, and the lower the number, the closer it is to the dam. So reach 1 is right up against Lewiston Dam. And that's where you see the highest pre-spawn mortality. Pre-spawn mortality can happen for a number of reasons. A lot of it has to do with the stress that the fish has undergone on its travels upstream. It tends to be higher earlier in the season than later. Water temperatures tend to be higher, more stressful environment during the migration. Tends to be lean towards more impacts to spring Chinook salmon because they spend longer in the river. They have a longer holding time. So by spreading the spawning out away from that area, from the dam, well, it could be just a chicken and egg thing, but there's, we've done a lot in the program to help ameliorate some of these issues. So as a summary for the adult stuff, so we've got natural origin Chinook salmon reds have been spreading downstream away from Lewiston Dam. We've seen an increase in the proportion of natural origin spawners. This is good. We want those fish spawning in the river to have come from the fish that were spawned in the river. We've seen a decrease in hatchery origin Chinook salmon reds out in the wild, and again, that just kind of goes along with the previous statement. And we've seen this decrease in Chinook salmon pre-spawn mortality. So even though we've experienced these declines in recent years of the Chinook salmon populations, we do have successes that we can point to, that are positive. So here I've got 4 positives, right? So now I'm going to transition to juvenile Chinook salmon. Again, just kind of go over time series, some relationships between adults and juveniles, and look at their size and immigration timing. This picture here is the lower trap at the Willow Creek trap site. It was taken quite a few years ago, but the place is still the same. So I'm going to start with kind of time series of, again, abundance and biomass. So if we look at the population estimates of juveniles from the Willow Creek trap site through time, we see a positive trend. So over, the entire time series. So this now starts in 1989. And so we've seen a positive trend, and that's a positive thing. We're producing, the system is producing more juveniles. But I mentioned before, there's the record of decision and the change in flow management. And so we did this analysis where we asked the data to impose a change point. So there's an analysis called change point analysis, and it goes through and it puts a change point in each of the years and determines which one fits the best. And it turns out that the best change point is basically right at where water management changed. So what we see if we break it out then into these 2 time periods, that the early time period and the later time period, we don't see a significant trend. So although this does appear to be trending down, it's not a significant slope. However, the overall mean is, more than 2 times greater than the early period. So I like to think of that as kind of like the fish bowl. We just gave them a bigger fish bowl. We can hold more fish. It's way more complicated and nuanced than that. But, again, I think that is my personal opinion, it's a direct reflection of the increased volume of water coming down in the spring period. If you recall back to the initial adult time series, and I made us kind of block out those high adult return years, you'll notice that those years for juveniles were some of the lowest abundance estimates in the juvenile time period. So in those years, although we got a bunch of adults back, the system produced very few juveniles. So it's just an interesting perspective, right? It's like, oh, things were better back then. Well, we got more salmon back, but was the system set up to produce juveniles? Not as well as it is now. So again, perspective matters. And again, more than 2 times greater abundance in the post-record of decision period. So that was just numbers of juveniles. I want to get into kind of more like productivity of the system. So one of the things we did was we looked at, took the average weight, or took the weight of all the samples that we got and converted the numbers into biomass. So this is in kilograms, and this is basically kilograms of juveniles produced per spawner. And what we see there is that although we, and again, this is not a significant trend at the 0.05 level, but we do see an indication that perhaps we're seeing an increased productivity in the system, so that per adult we're getting more juveniles. Now, again, this is a little bit of hand waving, and statistics are there's some subjectivity to that, I guess. So, but anyway, I like to think of that. I think we're going in the right direction. More water is good for fish. And again, so biomass per spawner, again, more than double in the. If you look at the mean across that period, it is higher than the previous period. So another way to look at the productivity is look at the stock recruit relationship. So in fisheries, this one thing we do to look at productivity is plot the number of juveniles versus the adults. And what we've seen here is kind of a state shift for pre-water management, or pre-record of decision to post, and that the curves in these stock recruit relationships has shifted upwards fairly dramatically from my perspective. You'll notice that I mentioned that we have this goal of 62,000 fall run. So this stock recruit is combined spring and fall run together. So these 2 black dots you see to the right of that are because we're adding in spring Chinook as well. Because at the traps, we can't distinguish fall run from spring Chinook. How am I doing on time? Okay, thank you. I look at my timer and I got a little nervous. So we've seen this upward shift in basically productivity. So again, that's a good thing. So I mentioned, we have a ton of data for over a bunch of years, and we collect a number of different things. One of the basic biological metrics or measures that we collect is fork length. And like I say, so I'm going to put this up. So this is called the violin plot. I'll just briefly walk through this. So if we look at this one here, you can think of this as a frequency distribution that's on its side and then mirrored, just to give it some heft. But you can think of the mean of this as the widest part of this violin. And so what I'm showing you here is pooled all of the fork lengths for non-clipped fish in blue and ad-clipped fish in red, pre-record of decision, post-record of decision. And so if we look at just the ad clip fish, so these are fish we know that are hatchery fish, and they're marked at about 25% mark rate. So we see there's been a significant decline in the fork length of the fish captured at the Willow Creek trap site in the post-record decision period. And at the bottom, you'll see the kind of sample size number. And I didn't put down the exact numbers because I was just kind of eyeballing it. But it's basically, more than 6,000 fish in the early period, more than 8,000 for those ad clips. And we go to the non-clips, which does include some hatchery fish because we can't distinguish them. They don't have a mark. But we see also a significant smaller size, shorter fish in the post-record decision period. I don't know if this is a bad thing or not. I definitely have. This is not something I'm celebrating as a positive result. And we look a little more detailed in this, and this is a very busy graph, and I don't expect you to get all the details in here, but this is essentially plotting those pre-record decision and post-record decision fork lengths distributions by week on the same plot. So the dark bars are pre-record decision, the lighter gray are post-record decision. And what we find is that in these early weeks, we're actually seeing a little bit bigger, longer fish post-rod compared to pre-rod, but that in the bulk of the weeks, the post-rod fish are shorter, smaller than the pre-rod. Some of this could be due to a density effect. We're producing way more fish than we did in the early period. It could be density. It likely is influenced by temperature. You'll notice there's a kind of a bump and then a decline. And that bump basically represents the appearance of the hatchery fish that tend to be larger in size than the natural fish, just because they're fed at a higher rate. But there's been an effect on fish size. Again, another figure that we're going to talk about emigration timing. This requires kind of a lot of explanation. What we do is we have years on the y-axis, starting from 1990 going up. And so the more recent years are at the top. The colored values are stream flow at the Hoopa gauge. So the red values are lower stream flow. The greens and blues are higher stream flow. The triangles and the squares happen to be the estimated emigration timing. So at which point in the triangles, 50% of the population has come past, and the squares, 80% of the population has come past. And you'll notice that there's those triangles and squares kind of line up along that transition between the green and the red. The point of this is that flow impacts timing. And when you have areas where really wet years, emigration timing tends to be later in the year. And dry years, emigration timing tends to be earlier in the year. So again, these are effects that flow management has had on salmon at kind of the population level. Is Tim Hayden here? I didn't see him. Anyway, Tim Hayden and I way a long time ago kind of recognized that. And then he and others started down this road of like looking at the effects of temperature on emigration timing. And so this is sort of abundance estimates of juvenile salmon on the y-axis, and then accumulated thermal units on the x-axis. So this is accumulated thermal units, basically like you just add whatever the temperature is for this day to the next day, and you just kind of add them up through time. And so what you'll notice is that the more accumulated thermal units you have, so to the right of this graph, the fish leave earlier. in the year. So this is okay. So the what's on the y-axis is the day of the year that 80% of the population had passed by. I misspoke earlier. So the cooler it is, the longer the fish stick around, the warmer the water is, the quicker they move out. So a summary for the juveniles. We've seen a significant increase in abundance, biomass per spawners after the implementation of the record decision flows. We've seen the state shift in productivity and stock recruit relationship. And we have seen that mean fork length of juvenile Chinook salmon is significantly smaller. It's not a huge amount, but it is statistically significant. And I put this one as sort of a not necessarily good or bad, but the immigration timing is related to flow and or temperature or some combination of both. But there is some covariance between the two. But that we are trying to incorporate that into our management, knowing that those are related. So with that, I will end on the joys of trapping.